full 360 degrees around the inner circle, it will touch again.
So anything that fibers into a bunch of strands, the strands will move around each other like circles, right? But that tendency to wrap around each other would form this shape, no matter what. Any two circles of same size rolling around each other trace out that shape if we pick one.
Utilizing one single point. Yep. Okay.
Oh. Those are some really pretty colors. Hey guys, what's going on? Memes here, as I'm totally not lagging out. Maybe I should actually hook up the things rather than using Wi-Fi. But, so the other day, Fractal Woman, she has a very interesting model of conceptualizing the stuff and things within our realm of persistence, what we may colloquially refer to as universe. So what we're going to do is I took a look at her papers, and it seems like she noticed something that was quite interesting. Take it away, Fractal Woman.
One particle as a concept is an expose on the fractal nature of the universe. In other words, I am trying to expose the fractal nature of the universe through my research and through my art.
So I actually just noticed something. There seems to be times when she does some videos where there happens to be a particular echo. Perhaps some may say a resonance, if you would. I may see what you did there. I have no idea whether it's impedance just from a shorting out mic or if that was intentional. Well played. But so basically she had posted links to a couple of her papers and everything. So I took a look at it. Why? Because I could. And she brings up some very interesting points, especially when you're talking about things like, oh, we had these dimensions, and when you set things up, and she's like, well, isn't it really just frequency? Isn't that like what we're talking about? Isn't that why like the Planck constant has like a circle in it? I'm not saying that that's why. It sounds like there's a rotation or something going on. Then with the and at one point she brought up, well, we also don't put one in front of things, which sometimes just can, at least for my brain, it can help make a difference. I see you there, guys. Thank you for joining, Kotov, Jupiter as well. But it's very interesting. And the claim is, back in like 1985, she wrote a program to explore the Mandelbrot set and basically take pictures so far in there at certain points, and she ran it overnight because apparently it was a very computationally heavy program, and apparently she found some interesting things. We were looking at it, it's kind of like, okay, we have things like galaxies and stuff like that, and you start seeing these different things. It's like, all right, and some of these things, they were seeded, but it's just very interesting how something very simple, just a very simple set of rules, can generate quite complex behavior. I feel like she should submit this to the Journal of Complexity from Stephen Wolfram, whom Professor Carroll cited in his recent paper. It's a fascinating world. Welcome, Fractal. Thank you for joining, my friend. But, okay, so this was her first one, and this is the new paper, I believe. It's... oh my God, I'm not even presenting. I'm a terrible host. All right, let's go to window. Boom. All right, there we go. All right, so the first paper was, yes, look at those pretty pictures. Okay, you notice some interesting things, and maybe there were very particular seeds to get these things, but some of these look like, I don't know, galaxies, nebulae, and stuff like that. And it's like, okay, that's interesting. It's kind of like when you look at the galaxies and the interstellar medium, and you look at it and you see these pictures, and then you see pictures of like the human brain and like neurons going together, and you're like, that's interesting. It's totally not related. So we go to the new paper here. This was what really sparked my interest. And again, this is conjecture on my part here. Total conjecture. Hold on, I think we need... did we run the disclaimer? I forget. But these things happen. Drugs are bad. A unified model of the universe. So she's going through here, and it's just very interesting, because this is the first time I noticed this. I'm sure other people have. Right? Okay, she's going through the constants, which I don't know if one is, and again, I believe she has education stuff in like what is it? Sonogram things with like magnets and computers and stuff, I believe. Um, correct me if I'm wrong. So basically, you have Planck's constant, the gravitational constant, the speed of light. You have elementary charge, and those are measured values. And then we have derived constants, such as the magnetic constant. Yes, we have not over there at K and M over that. Yeah. Oh, look. Oh, times 10 to the negative 7. Oh, it looks like. Oh, I think these are ones she derived herself. Well done. But I'm sorry. I shouldn't snicker. I'm just. It's a fascinating world. Hey, Dan. Thank you for joining, my friend. All right. So basically, the whole thing right here. It's this. It's this. That's why it was on the thumbnail. Oh my god, why won't it let me highlight? Okay, just zoom in. When you notice, apparently Coulomb's constant. Now they just call it, I believe, the electric constant. You have these numbers, and you take a look at the speed of light squared. Those look very similar. There's one thing I learned from Thad. It's every once in a while, if you notice something, if you have the ability to explore it, why not? What if we assumed it was true? And if it wasn't, might that be even more interesting? So, all right, the claim is, as you can see here, and then I believe it's the speed of light because we have it to 9 significant digits. So that's very interesting. What is this? This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, I think we do have the magnetic constant or Coulomb's constant to 10 digits with the redefinition of SI, because I think Planck's constant is to 10 digits now. Maybe 9, maybe 11. I forget. I did a video on it. But, okay. Why is this interesting? And again, this is just me. Okay. You know, speed of light squared. We get these numbers here. All right. So basically, you're looking a little under 9 times 10 to the 16. That's cool. Go to Coulomb's constant. Oh, it's so pretty. 1 over 5 times the electric constant. I'm just imagining like a little whirls and everything like that there. Okay, so you get this number here. It's a little under 9 times 10 to the 9. Oh my God, we're off by what? 7 orders of magnitude? That's not good. There's also another thing that she noticed. Because, okay. Notice the magnetic constant is exactly 10 to the negative 7. Have we seen that before? Pardon me. What if there was a combination, let's say hypothetically, like the Planck mass, maybe the Planck Planck length, and let's say we divide it by the Planck charge squared. So we do the Planck charge raised to the -2 because we want it in the bottom half, the denominator. It seems like an interesting thing to put together, so we actually got to do multiplication. Okay, what's that? Oh, 1 times 10 to the negative 7. Oh, it's 1 Ampere's constant. Groovy. We continue. So basically, the whole claim is what is the claim? What if we could get some more significant digits? Because we notice right there, it's like, all right, we seem to be skipping ahead. We can get out to that many digits there. Okay, what if we get basically what happens hypothetically if we actually have the exact numbers? Might there be an interesting connection? There may be, I postulate. I'm not going to make a claim. It's just interesting. Okay, we move ahead. So what is this? All right. The claim is this is a geometric derivation of the speed of light using the universal binomial factorization equation. What the heck is that? All that is basically you have stuff. So basically your dimensions are undergoing different things. and we break that up. So basically, you might have an action which might be 1. In this case, for the speed of light, it's 1. I think that's something we do in physics already. And again, I am not a professionally trained physicist. I'm a dude on the internet I'm blessed to listen to and talk with some really smart folks. So basically, you have a primary action, it's 1 here, times your boundary conditions, which would be the dimensions, which when one goes down the Wolfram hole long enough, one realizes that basically the constants of nature, as far as dimensions go, you can make them up from time, space, charge, mass, and temperature. 5. That's very interesting. So in this case, what do we have for the speed of light? Oh, no, excuse me. This is, oh, wait, no, that's K. What am I doing? Oh my God, I'm showing the wrong constants. I apologize. Where are we? Okay. That was the wrong thing. All right. I apologize. Oh, no, that was, no, that was just totally wrong. I apologize. Live internet. All right, here's the speed of light. Planck length divided by Planck time. The primary action is 1. And then that's, that previous one was kappa because it was the K, kappa. So that's 1 plus, because we break it up. So primary action, Planck length divided by Planck time. That gets us up like 7 significant digits. The corrective term would be in the terminal action, because one notices at that 10 to the negative 7, constants in nature seem to, I'm not saying that's why they had to redefine SI. Was it? But, okay. The terminal action is going to be 1 plus whatever the action is usually going to be some zhuzh, like the fine structure constant, something like that. There's a geometric action times the inversion boundary, which is the 10 to the negative 7, which happens to be that little box in the corner there. The primary action for that, terminal action for the speed of light happens to be the square root of the Giesecke constant times Zh1 minus Zh2. We did a video on the other day on how you can hack the universe using Wolfram alpha. But it's very interesting. Well, Fractal, to see the interesting thing is with that, we're also going to be 5 platonic solids. Connection, I guess we're going to have to see. I'm also a big nerd. I love Dungeons and Dragons, so I'm totally biased there, even though we throw in a D10. So where are we going? Okay, so again, the claim, what if we actually have these numbers to as many decimal points as we wanted? Might we notice something? That's the whole point of this video. It's taken me over 13 minutes to get into. Okay, so this is geometric derivation for the speed of light squared, using basically Thad's model for the minimal arena, or the HF8 model. All right, so that's about 9. 1 to 9 times 10 to the 16. Okay, that seems to line up. Okay, that's 10 to the 16. We got those numbers there. Cool. We go. Oh God, where's the magnetic constant? Okay. Should be. Oh God, did I leave you? Where did I leave you? Oh, did I close out that window? That's terrible. No, this looks like it. There we go. Okay. This is oh, here we go. Magnetic constant. So, because it's 10 to the 9. All right. No under 9. What is this? We got the Planck length cubed times the Planck mass divided by, that's Planck time, because negative 44, that's squared. And that's multiplied by the Planck charge squared. Okay. So those are our dimensions using, we get those numbers there. Okay. Do they line up? Spoiler, they don't. But what I found was interesting. And again, just complete conjecture. So that's our speed of light, according to the model we've been working with at the monastery. Okay. So the speed of light squared, what happens if we multiply it by the electric constant? That basically 10 to the negative 7, or Ampere's constant. Or, within the HF8 model, the minimal arena, the inversion boundary is the claim. Okay, we get that number right there. So when we take those numbers, we got that number there. We got that number there. Wait a second. Let's zoom in a little bit. So we got 8.98755179124446. Cool. Let's go to the other one. Let's do the quick changeover so we can actually notice. Okay. Okay. Oh, it seems to be different after the 9. 3, 2, 3, 2, 8. I realize these numbers mean absolutely nothing to anybody, but there was just a very interesting thing that I noticed. And again, probably nothing, but when we see the difference there, we get this number here. Okay. 1. Oh, that's almost 2. That's pretty neat. 1.9862. Okay. And if we do it the other way, we get the negative version. Negative 1.9862. Is there any significance to that number? With what I've learned at the monastery and from Professor Wolfram, sometimes exploring the computational universe, perhaps for a closed form, may give us some intuition. Hey, Rick, thank you for joining, my friend. It's very interesting, some of the things going on. Again, probably nothing, but when I did search for a closed form, I'm like, okay, was there anything cool here? Da-da-da. Oh, E, right, so the 1 divided by E plus 1 divided by pi. Okay, that's cool. That's kind of close. It's 4 significant digits there. I thought that was kind of neat. I love the relations between E and pi, but I'm going to have to claim Euler's is probably the best. Euler. As he strikes again. All right, oh, E squared divided by 1 plus E. Oh, that's cool. 3 significant digits. Oh, look, we got 4 pi. Oh, 57. Oh, logs of pi. Da, da, da. Cool stuff there. Da, da, da. Wait, what? Well, these are kind of cool. These are, I think, tetrahedra volumes and stuff like that. But wait. This looks a little familiar. 3 times the square root of RE with the PPT gives us 4 significant digits there. Oh, and that's kind of close to, is it a 1 or 2 we needed there? Okay, 2. What is that? Good thing we have Wolfram Alpha. Okay, so what do we have there? Oh, RE Z is the real part of Z. Fractal Woman's been talking about the Mandelbrot set. Isn't that like Z squared or something? Neat. PPT is the value of the infinite tower power of I. Huh? Power tower. Power tower in the order of K is defined of A. Basically, you just keep on raising whatever it is to what it is. In this case, this happens to be I. Wasn't I something about like kind of like zooming around or something like that? That's interesting. So what's also interesting is when you take the negative, basically you kind of get the same thing. Oh, look, well, that's, negative 2/5 pi. Oh, look, it seems to be here again. The negative version. And what is this again? What are we talking about? 3 times the square root of something. The whole point of our paper was to kind of point out, it's like, might there be something going on within the vacuum, space and time vacuum, even though there's quantum fluctuations and stuff and things apparently going on? Is this something like, don't we have like 3 spatial dimensions is the claim? Some string theories, 9, 10, something like that, but 3 is the square root of something that's real, the infinite tower power of I. There's a reason that stood out to me. Thad, what might be going on here? Wait. Okay, I realize there's no audio. We don't really need the audio for this. So this was some of the updated chemistry and constants of nature. Wait a second. Oh God, the resolution is terrible. Oh God, it is terrible, or at least the CRT level. Okay, here we go. Wait a second, what's this? Oh, that's Z naught. Wait a second, isn't that the electric constant? The von Klitzing constant? Huh. Wait a second, 4 pi. Okay, we that's not the point. Don't worry about the primary actions there. What I'm interested in is the construction here is the terminal actions for these are 1 plus half the real infinite tower power of I. Oh, and that's Ja R. That's basically the radius of the hyperbolic vortex. I believe it's throat. I could be wrong there. That's squared. It's cool. 1 plus. Oh, it seems to be a pattern here. So, RK. All right, angles. 1/2 the atomic velocity. The atomic magnetic moment. What is it? Oh, the mass of the electron times the speed of light. Okay. This is energy. I believe this is the energy mass. I believe that's the energy mass. Yes, because it's got the mass of the electron, mass of the proton. Okay, I believe that's the energy mass equivalent of those different constants. Oh, it's still going on. Huh. Yeah, a lot of these are just inversions of each other. So, I mean, that's one of the reasons why it's larger. Full disclosure. Oh, the Triton. Okay. We got mega electron volts. Okay, there seems to be something with energy here. Huh. Wait. Hold on. Wait a second. Was that the kilogram times the speed of light squared? The kilogram. Oh. Now, I'm not saying that there's anything actually there. It's just one of the things we were assuming when we took a look at Fractal Woman's paper. This seems to be a very interesting coincidence. These things seem to line up really well. So let's assume they're true. But we only have measurements to a certain level. Hey, Gap. Good to see you. It's very interesting things going on. Oh no, hey, oh, happy birthday, Rick. Happy birthday, my friend. It's hopefully you have many tasty snacks. And maybe even a main course. But I just found it was interesting that something, if we're going to be looking at what might be, I don't know, correspondence between the speed of light squared, which we seem to use that for a lot of things within science, and the electric constant, aka Coulomb's constant. And at least according to the monastery's model, you look at it, it's like they appear to be off based upon the current derivations. Might there be better derivations out there? Totally. I'd be happy. Let me or Thad know if anybody finds any. That'd be totally sweet because, well, we're looking to do some really cool stuff. I mean, universal replication is the goal. I mean, can we get that there within our lifetimes? I don't know, but it could be very interesting. I don't know. I'm just imagining like infinitely spiraling board. Is this how space-time itself as we know it comes together? I don't know. I just noticed a lot of things regarding energy and basically Fractal Woman's paper that she did, which links are in the doobly-doo. Feel free to check them out. It's actually not even that long. Even Professor Carroll's paper today was only like 8 pages. Not every paper is like 120 pages. Well, I think that's pretty cool that we have the internet and the ability to communicate with one another to try to figure out what's going on. Because we can. And I think it would be really neat. So that's all we got for right now. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there, but I think the best is yet to come. Be safe, everyone.